7.1 talking about relations and functions. And if you recall back in chapter 6, I talked about that rational expression, capital R of x. So we're finally going to get to experience that notation here. So first things first, we're going to talk about a relation. A relation is a set of ordered pair of points x comma y. So these are points that we plot on the xy coordinate plane. Every x has to have a y and every y has to have an x. What we want to do is see, can we take this relation and upgrade it to a function? So a function is going to be an ordered pair of points, a relation, such that, here comes the restriction, every x coordinate in the domain corresponds to exactly one y coordinate in the range. All right, so you saw the word domain. Domain means this is the set of all x coordinates. So we're going to take all our points, take all the x numbers, and put them into its own individual set. Then we're going to take the range. We're going to take all the y coordinates, take them out, and put them in their individual set. Now, what does it mean to be a set? A set has braces at the beginning and end. So this right here, this example, is a set of ordered pair points x comma y. Now, if I want to see, it's going to be a relation. It's automatic relation because it's a set of points. So that's a given. What we want to do is, can we upgrade it to a function? So we know it's already a relation. Can I upgrade? So the definition, every x must correspond to exactly one y. So the focus point is check your x coordinates. 1, a 3, a -1, a 4, another 3, and a 5. Wait a minute, let's check these two out right here. The 3's repeat, and they have different y coordinates. So we cannot upgrade this to a function. This stays as a relation. It's not a function, it's just a relation. Now, sometimes authors like to trick you and put a 3 comma 1 and another 3 comma 1. It's the same point. It's the same x with the same y. That would be considered a function. All right, our next set of points, we check out our x coordinates, 1, 2, 3, 4, 5, 6. They're all different, no repeating x's. This we can upgrade to a function. The next way they'll write this out is they're going to give you what we have here, our charts or tables, or I don't want to say a corresponding table, if you will. Traditionally, the rectangle represents the domain, so these are all the x coordinates. The oval represents the set of all your y coordinates. So what we want to do is compare, do the exponents, or excuse me, the x coordinates in the domain only have one corresponding arrow in each x coordinate. All right, so here's 1, it corresponds to 14. 2 corresponds to 11, which means this would be the point 1 comma 14, 2 comma 11, 3 comma 14, 4 comma 12, 5 comma 13. This is a function. Every x coordinate corresponds to exactly one y coordinate. We said it's okay for the y coordinate to repeat, so this is a function. All right, down here, looking at this domain, looking at this range, the first dead giveaway that you notice is that the 8 has 2 arrows coming out of it. Therefore, that is not going to be a function. It's going to stay a relation. All right, now, there is a trick question that I have to show you. So let me get my iPad up here and running. It should be popping up here real soon. There it is. Okay. So here's the trick question. And I'm going to kind of use this first one right here. I can cover that up. Doesn't matter what numbers I use. Come on, make it bigger. There we go. Okay, so here's my domain, my box. 1, 2, 3, 4. And I'm going to be honest, I actually heard a teacher say this one day when I was walking past the classroom. And of course, I had to call them out. And this was their definition. They said, all you have to do is cover up the range and look at your x's. And they say, look, if there's only one arrow coming off of every x, that's a function. If there's two arrows, that's a range. It's not a function. And I'm like, whoa, 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 whoa. That's not what the definition said. So I sent her I apologize, it was a her. I sent this teacher this following diagram. So I put in here, okay, let's say 6, 7, 8, 9, and 10. And then I drew arrows and I said, well, based on your definition, what I heard you say in class, this is a function. But we got a problem. Nobody is corresponding to the 9. Now here's the kicker. Based on what this instructor said, this was going to be a function. However, this is not a relation. Oops, T-I-O-N. All right, because I can write my points. 1, 6, 2, 8, 3, 10, 4, 7. Who's matched up with my 9? This is not a point. So if I don't have a point, I can't even have a relation. So there's no way this can be a function. So don't listen to anybody who says, oh, you just have to look at the arrows. No, you don't. You got to see where the arrows go to. If we have a missing value not matched up with, it's not even a relation. So watch what tutors tell you, some instructors tell you. Some people like to come up with shortcuts and they don't always work. Okay, so be careful. All right, next we're going to look at graphs. All right, so a little trivia question here. I want you to look at this first graph. I'm going to see how well you're thinking. How many points do you see in this graph? You have 3 seconds to come up with an answer. 1001, 1002, 1003. All right, commit to an answer. Did you say 5 points? If you did, you're wrong. I know you see closed dots, which do represent points. But any spot on these line segments are points. So there's a starting point, a turning point, turning point, turning point, end point. But there's also an infinite number of points between that end point and this end point. Infinite number of points here, here, and here. So there's infinite number of points. The only way this could be 5 is if you had this point, this point, this point, this point, this point, with nothing connecting them. All right, so keep that in mind. All right, here we go. When determining if a graph is a function, we use the vertical line test. Now, what we're going to do is we're going to use your pencil as the vertical line. We're going to place it at the far left of the graph, and then we're going to slide it across the graph. As you slide the pencil to the right, and if you see it touches the graph only once, if it does it is a function. So if I take my pencil and I slide it across once, that's a function. If I look at this graph and I slide my pencil, I can already see right here what happened to my sliding of my pencil. I lost my pencil here. Boom. There's the slide. What happened to my sliding pencil down here? There it is. Slide, pencil. Oh, there it is. It's all automatically. Right here, it stops. You can see it touches the graph in 3 locations. It's only supposed to cross it once. So you can even see from the y-axis, 1, 2 points. 2 or more, it's just a relation. Okay, evaluating functions. Functions use special notation called function notation. And as I told you about that capital R of x back in chapter 6, f of x, it's not multiplication, it's f of x. That's the way we read this. And it's important to understand that it represents the y coordinates. So y equals f of x. The x is also known as the input, and y, or f of x, is known as the output. The phrase y is a function of x means y equals f of x. You take the x coordinate, you put it into the function, whatever this expression might be, you simplify it, and the output becomes the y. It's important to understand that in this phrase, y is a function of x, whatever letter is before the word is the dependent variable. The dependent variable depends on the x variable for its value. So the x is then known as the independent variable. I can be anything I want, but the y depends on the independent variable. Now, you might remember problems like this. Find the value of y for the equation y equals 3 of x plus 7 when x equals 4. You took the 4, you substituted in for x, 3 times 4 was 12, plus 7, 19, and there's your answer. All right, so a lot of students ask me, well, why do we have to know this function notation? 2 reasons. 1, it makes the problem easier to write. This above problem right here, all this right here, can be simplified as this. Given f of x equals 3x plus 7, evaluate f of 4. Notice 4 is in the position of x. That's the x equals 4. Remember, y is the same as f of x. So here is y equals 3x plus 4. This says put 4 in every place you see an x. So 12 plus 7, 19, we're done. The work is exactly the same. It's just that as math teachers, we don't like all this verbiage. We shorten things up. The second thing it tells us is that, remember, the definition of a function says that for every x you input, you are guaranteed one and only one y coordinate. So you're not going to get 2 different y coordinates for an x. That's what you're guaranteed with that notation. All right, next we got, well, let's try this. Let g of x equal x squared plus 5x minus 3. Evaluate g of negative 6. So every place you see an x, you're going to put parentheses around it, and then you're going to put negative 6 in for all the x's. And then you simplify it. So negative 6 squared, negative 6 times a negative 6, is going to be a positive 36. 5 times negative 6, negative 30 or minus 30, minus 3. All right, simplify. 36 minus 30 is 6, minus 3 is 3. That's my answer. And it's also important to understand, this also represents a point. This is the point, left parentheses, negative 6, comma 3. X coordinate, y coordinate. If we want to find g of 10, we do the exact same thing, parentheses around your x's, and then put 10 in for all the x's. So g of 10 equals 10 squared, that's 100, plus 5 times 10, that's a 50, minus 3. 100 plus 50 is 150, minus 3 is 147. Again, this would be the ordered pair point, 10, comma 147. Now, notice we can also use variable expressions. So if you're going to put in a 3t, your answer has to have t's in it. Notice here's my g of x function. If this is an x, everything has an x. The work is exactly the same. You put parentheses around every x, and you take out the x and you put a 3t in its place. So we're not going to come up with a value. If you start with a value, you finish with a value. If you start with a variable expression with t in it, you must end with a variable expression with a t in it. So 3t times itself 3t, that's 9t squared, plus 5 times 3t is 15t minus 3. There's nothing to simplify. I can't combine anything. You're done. This was actually easier than to do this one, because these were numbers and values that I can combine and simplify. Here, no like terms, I stop. G of b plus 2, same thing. Parentheses around every x. Now you put the b plus 2 into every set of parentheses. So this indicates here, what's wrong with my mouse? That b plus 2 is a binomial being squared. So all right, you're going to have to FOIL this one, and here you're going to have to distribute the 5. So b plus 2 times b plus 2, we're going to get b times b is b squared, b times 2 plus 2b, 2 times b plus another 2b, 2 times 2 is 4. So this simplifies to b squared plus 4b plus 4. All right, there was my FOIL work. Here's where I'm at. Distribute the 5, 5b plus 10 minus 3. Now here we have some like terms we can combine. Only 1b squared, but 4b plus 5b, that's a 9b. 4 plus 10 is going to be 14 minus 3, which gives me the 11. All right, next example. You can have a function h of x equals a set of points. Now what that means right now, because they're using function notation, there should be no x's that repeat. 1, 2, -1, 4, 3, 5. All different x's. Evaluate h of 3. All right, so remember, h of x, your function name has to equal the y. Doesn't matter if it's an f, a g, an h, a j, a k, doesn't matter the variable name. So I'm going to take h of 3 and say, okay, I have to equal y. So 3 is my x coordinate. So I go up to my list, I'm looking for a 3. Nope, that's the y coordinate. Keep going. It's right here. So if x is equal to 3, then what's my output y coordinate? This 2 goes in for y, and you're done. H of 3 equals 2. All right, let's try h of 2. Well, go right here, right above it. There's the x coordinate of 2. Bring back the y coordinate of 1. H of 2 equals 1. We're done. H of 0, let's go find a 0. Wait a minute, there's no 0 here. All right, so therefore, since 0 is not in the domain of our x's, it's not in our function, then there cannot be a y. So this is called an undefined value. There's no 0 in the domain. It doesn't correspond to any y, so we call this undefined. Now, some authors in their books, they'll say use the letters D and E for does not exist. That's the same thing as undefined. So those are interchangeable. Now, we can also have a function that's a graph. Here's j of x, and if you look at your vertical line test, it passes. So it's a function. And they're asking us to do the same thing. Find j of 3. It has to equal y. So you go find the x coordinate of 3. Here's your x-axis. We go to 1, 2, 3. Here's the 3. You go up until you hit the graph. There's this point right here. 1, 2, 3, 4, 5. I'm at the point 3, 5. So return the y coordinate of 5. You're done. J of -2. We're going to go to -2. That's right here. We're going to go up until we hit the graph, which is this point right there. I went up 1 square. That puts me at negative 2 comma 1. So that's going to be my output, a 1. J of 0, here's the origin. We're going to go straight down with our 0. That puts me at the point 0 comma negative 1. Return the y coordinate of negative 1, and there's our answer. Same graph, but notice the difference here. Now this was j of 3, we had to equal y. Now notice it says j of x is equal to 3. So 3 is actually in the y position. And notice it says find any x values. It's plural. There can be more than one possible answer. So as we go up on the y-axis to 1, 2, 3, here's my 3. I'm going to go to the right. I hit this point. My x is at 2. This is 2, 3. So I'm going to return the x coordinate of 2. There's only one place that happens. That's fine. All right. Next, j of x is equal to 1. So now we're going to go to 1 on our y-coordinate, but holy smokes, hold the phone. We can go to the left and hit 2 points, and we can go to the right and hit a point. There are 3 points that have a y-coordinate of 1. 1, 2, 3, 4. At negative 4, 1. At negative 2, 1. And at 1 comma 1. So we have 3 answers for x. Remember, this was plural. So x equals negative 4, negative 2, and a 1. Next, we're going to have j of x is equal to 5. All right, that's my y-coordinate. Let's count up the y-axis. 1, 2, 3, 4, 5. We're right here. But holy smokes, we have this point, and everything in between. So that means 3 will work, 3.1, 3.2, 3.001, 3.002. I have an infinite number of x's here. I'm not going to write them out all individually. So I need to come up with a way to express, I want every x coordinate from 3 to 6. So there's 2 ways to do that. We can write it as a compound inequality. 3 is less than or equal to x, less than or equal to 6. That means I start at 3, I can touch the 3, and I can touch all the x's between 3 and 6, including 6. That's a compound inequality. If they ask you for interval notation, then it's left bracket 3. Brackets are used when you have an equal to line. If there is no equal to line, then it's a parentheses. So left bracket 3 comma 6, right bracket. That's the interval that notation that means this. So this again says I'm including 3 and everything up to 6 inclusively. That's my answer. All right, j of x equals negative 3. Let's count down. 1, 2, 3. Here's negative 3. But I look to the left, I look to the right. There's no points here. So if it doesn't exist, it's not possible. Undefined or DNE for does not exist. And that wraps up 7-1.